Hi everyone, this is lesson 1-3. We'll be discussing continuity and behavior and limits, and our learning target for this video is for students to be able to apply the intermediate value theorem to continuous functions. Key concept number 3 is the intermediate value theorem, and what it analyzes is a continuous function f of x where a is less than b. Note that A and B are marked on the x-axis of the graph. And if A is less than B, and there is a value n such that n is between f of A, so this is our y-coordinate paired. So if we had A as our x value, f of A is our y-coordinate. And for f of B is our y-coordinate when x is our, when b is our x-coordinate. So f of b here is our y-coordinate when b is our x-coordinate. And then there is a number c such that c is greater than a but less than b, and f of c is equal to n. So basically what they're looking at here is, basically if this x value, or the x value is denoted as a, and we have its y value right here, which in this case on this graph, if the origin is located where it is, this a value right here going down to the function, which is this blue wavy curve here. So here's our function, the graph of our function, which is this wavy curve. And if we have this a value right here, and we go down to the graph and across to the y-axis, our y-coordinate would be f of a. Now, a we know is less than b because b is farther to the right on the number line than a. And if we go up to the graph at b, we will have a y-coordinate named f of b, the function evaluated at an x-coordinate of b. Now, what we're going to have is c, which is in between a and b. So c is greater than a but less than b, because c is to the right of a but left of b. And if I go up to the function and over to the left, we get f of c, the function evaluated at c. Now, what happens is because because c is in between a and b, then f of c has to be in between f of a and f of b. Now, the corollary to this is called the location principle, and what it says is if f of x is a continuous function and f of a and f of b have opposite signs, meaning one's positive and one's negative, then there exists at least one value of c such that c is greater than a but less than b, and f of c is equal to 0. So therefore, there is a 0 between a and b. So what they're saying here is that if you know that an x value of a is negative and an x value of b produces a positive y-coordinate, okay, so a produces a negative y-coordinate, meaning f of a is negative. And I know f of b, the second b is my input, but f of b would be my y-coordinate, and I know f of b is positive. Somewhere in between these two values right here, there has to be a 0, because we're switching from a negative y-coordinate to a positive y-coordinate, so we're going to have to pass 0 on the way from switching from negative to positive. And that's what this location principle is talking about, that when you have a y value, f of a, that is negative, or vice versa, if f of a is positive and f of b is negative, we could have this the other way. If f of b was negative and f of a was positive, in between these two values here, when we're switching from a negative y-coordinate to a positive y-coordinate, we're going to have to pass 0. Because on a number line, when we switch over from negative numbers to positive numbers, we pass through 0. what we're going to do in example 3 is we're going to approximate zeros, and we're going to use the intermediate value theorem that we just discussed on the previous slide to determine between which consecutive integers the real zeros of the function x squared minus x minus 3/4 are located on the interval of -2 to 2. Okay, so what we have here is an x value of and an f of x value here. And we are going to locate all the real zeros between -2, which is our minimum, and +2, which is our maximum. Our minimum x value and our maximum x value. So what I'm going to do is I'm going to fill out my table here from -2 to +2. So I'm going to go from -2 to -1 to 0 to 1 to 2. And I'm going to find the y values that correspond with each of these x values. So what I'm going to do is I'm going to type this equation into my graphing calculator, and I'm going to once I have this typed into my graphing calculator, I'm going to go to my table, make sure my independent variable is on ask, and then fill in these x values from -2 to +2, and then record my y coordinates that correspond with each of these x coordinates. After graphing my function on the graphing app on my iPad, I can see that my table is given here. I've cropped out a picture of my table from my graphing calculator, and I'm just going to slide it over here over the top of my hand-drawn one because this is a little neater. And what I can do is I can analyze now what's going on in the table. Notice that my x value has a minimum of -2 and a maximum of +2. And here at -2, my y coordinate is positive, and my x coordinate is at -1. My y coordinate is also positive. And then all of a sudden at 0, an x value of 0, we switch to a negative y value. So if we are switching sign here from a positive to a negative, that is telling me that somewhere between 1.25 and -0.75 is the number 0. And so therefore I have a 0 somewhere in between an x value of -1 and 0. Meaning we're crossing the x-axis somewhere between a -1 and 0. And so here we go over here. Our y at 1 we're still negative, and then at +2 my y coordinate's positive. So since again we're changing sign here from negative to positive, we have a -0.75 and a positive 1.25. Over here, we know in between these two values is the number 0. 0 is greater than -0.75 but less than 1.25. So therefore, I know I have a 0 on my graph between 1 and 2. So it says the question asks us to determine between which integers the real zeros of the function are located on this interval between x equals -2 and x equals +2. And I'm going to say one of my zeros occurs at in between -1 and 0. My 0 here, my y coordinate is 0, somewhere between an x value of -1 and an x value of 0. And again, we have another 0 in between an x value of +1 and +2. Now what I've done is I've screenshotted our graph just to show you a visual of where our zeros are at, and to confirm that for sure we have a 0, which is an x-intercept, somewhere between -1 and 0. So here's an x value of -1, here's an x value of 0, and sure enough, the graph crosses the x-axis between -1 and 0. And also, if this is x equals +1 right here and x equals +2 here, we have another 0 right here where the graph crosses the x-axis in between 1 and 2. So we can use the graph up here to indicate that the zeros are in between the values we have determined using the table. So to summarize, what we're saying is that our zeros of our function occur between an x value of -1 and an x value of 0, as well as we have another 0 between +1 and +2. And again, here is our 0 between -1 and 0, and here we have another 0 of our function between x equals 1 and x equals 2. In example 3, part B, we're going to again approximate zeros for a function. This time we're asked to determine between which consecutive integers the real zeros of f of x equals x cubed plus 2x plus 5 are located on the interval between x equals -2 and x equals +2. So this time I am going to graph the function x cubed plus 2x plus 5. And I want to know in between an x minimum of -2 and an x maximum of 2. I want to know between these two x values how many zeros we have and on what interval they're located. Okay, after graphing our function on my graphing calculator on my iPad, I've produced this table of values such that x is between -2 and +2. And what I want to look at is where my zeros of my function might be located. Now, based on that location principle, the corollary to the intermediate value theorem, we are looking at where the y-coordinate is changing sign. Okay, we are changing sign right between these two values. 0 would be located, a y-coordinate of 0 would be located right between -7 and +2. Not exactly in the middle, but somewhere. We would have to, when we're moving from a value of -7 to +2, we would have to cross through 0 or pass through 0. And so therefore, my x values, the 0 of my function, occurs between -2 and -1. So the 0 of my function is somewhere in between these two consecutive integers. Realize that -2 is an integer, -1 is also an integer, and they're asking us to determine between what two consecutive integers the real zeros of the function occur. So I know that I have a 0 between -2 and -1. Now, what I'm going to do is I'm going to take a look at my graph to confirm that our 0 occurs between -2 and -1. Okay, here we have a graph of our function, and what we can see here is that our our 0 of our function, or our x-intercept, occurs between an x value of -2 and an x value of -1, because here we have the origin. And therefore, our 0 is between the integers of -2 and -1, because again, our x-intercept, or the 0 of our function, is right here. There's the x-intercept, which occurs between an x value of -2 and an x value of -1, which confirms that we had the correct answer based upon our discussion of the table. In example 3, check for understanding. I would like you to determine between which consecutive integers the real zeros of f of x equals x cubed plus 2x squared minus x minus 1 are located on the interval from -4 to 4. You have 4 choices, A, B, C, and D. Go ahead and work out the problem, graph, and provide a table, and then choose which answer you believe is correct, A, B, C, or D. In example 3, check for understanding part B, I would like you to determine between which consecutive integers the real zeros of f of x equals 3x cubed minus 2x squared plus 3 are located on the interval between x equals negative 2 and positive 2. You have 4 choices, A, B, C, and D. You are only asked to graph the function between negative 2 and positive 2, and then determine between which consecutive integers the real zeros exist. You have 4 choices, A, B, C, and D. Go ahead and graph the function and analyze the table, and then choose the answer that you think is correct.